Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Today I am so happy we can meet Professor Gorazd for this conference. Good morning, Gorazd.
Good morning.
Welcome to our conference. When I visit Slovenia 2018, Professor Gorazd showed his laboratory with various interesting laboratorium equipment. We also at that time discussed about this conference. Yeah, it's 3 years ago. STEM Research Center has strong relationship with Egina as USA partner, and Gorazd, since I meet him during Physics Week 2015 in ICTP, Italy for ISLE training. Okay, I will introduce you Professor Gorazd Planinsic. Please you prepare your presentation. Okay. Professor Gorazd Planinsic is a professor of physics at University of Ljubljana, Slovenia. Since 2000, he has led the physics education program, which prepared almost all high school physics teachers in the countries of Slovenia. He started his career in MMR physics and later switched to the physics education research. During the last 15 years, his work has mostly focused on the research of new experiments and how to use them more productively in teaching and learning physics. He is co-founder of the Slovenian Hand-on Science Center House of Experiment. Professor Planinsic is a co-author of more than 80 peer-referenced research articles and more than 20 popular science articles, and is the author of university textbook for the future physics teacher. In 2018, he received Gorazd Medal for his work in physics education. Okay, now Gorazd, this is your time for presentation. Thank you. Please.
Thank you, Irvandi, very much. I would like to first thank organizers for inviting me. It's fascinating to experience and to witness this amazing event that you were able to put together. I haven't been at such event before, of course, also due to reasons that we all know, but in this time to prepare something like this is really an achievement. I'm really honored to be a speaker at this conference. And so let me start with my presentation. I will share screen. I hope this is not yet, but soon visible. So, my name is Gorazd Planinsic, coming from University of Ljubljana, Slovenia, which is one of the smallest countries in Europe. And the title of my talk is New Types of Problems. Let me first explain what do I mean by new types of problems. I mean problems that go beyond the traditional problems where we ask students to only search for one particular numerical, usually numerical answer. So, or in other words, problems that can be solved only by searching for a certain equation or combination of equations. Or problems where we give students exactly the number of givens and assumptions that they need to solve this problem and ask for specific quantity. So if you look this, you will realize that most of the traditional problems are this type of problems. So new types of problems should go beyond this. Now, why do we need new type of problems? Let me show you this slide here. These are some random titles from recent news. And one thing that all these titles have in common is that they all speak about artificial intelligence. And they all speak about how artificial intelligence is affecting or will affect our jobs. You see, it's all over the world. They are replacing people working in banks. They are replacing people working in healthcare. They even think of finishing Beethoven's unfinished 10th Symphony using artificial intelligence and so on. So what's the message from this? Very simple message that those jobs that can be replaced by smart machines will be replaced by smart machines. And this means that in education, we really have to now focus on how to prepare future generations so that they will still be able to find jobs and that they will be able to also develop as human beings. Working is something that we all need. So the world is aware of this. And one evidence is that Organization for Economic Cooperation and Development in 2018 launched a position paper in which they described what kind of knowledge, skills, attitudes, values will today's students need to thrive and shape their world in future. What they say is that we will have to still continue to develop disciplinary knowledge. So, for example, knowledge of physics, biology, chemistry, the content knowledge. But because of without having this, we cannot even talk about something else. But in addition to this, our goal is to develop epistemic knowledge, which means learn how to think like physicist, biologist, historian, mathematician, and so on. And you would probably agree with me that you cannot learn how physicists think by reading books how Einstein was thinking or how Richard Feynman was thinking. The only way to learn how to think like physicists is to expose a student into a situation, into an environment that help the student to learn physics and to learn how to think like physicists. So we have to create very new environments in which we will also develop this kind of epistemic knowledge. But in addition to this, there is another imperative that we have to also develop procedural knowledge. This is knowledge acquired by understanding how something is done or how some things work, and typically requires practical problem solving. In other words, for example, for science, this means how to integrate engineering components into the classes of physics or chemistry or biology, another challenge. On surface, we would think that engineers and scientists are using the same tools, so they might be using the same reasoning, but it's not true. Goals, their strategies of solving problems are different, and one goal is to incorporate that in the science. So I will show you through the rest of my talk several new types of problems, and I will also briefly discuss why these problems are good, what is the benefit from these problems, what are these problems helping students to develop. But before going to that, I would like to say what is common to all these new problems that I will show you. All these problems that I will show you were developed for the materials that follow a learning system called Investigative Science Learning Environment, or short ILE, which was created by Eugenia Etkina, Radgers University, and later also improved added to it by Alan van Heuvelin and others. Here, I'm lucky that Eugenia already had talk before me earlier this morning for you. So she already set the stage. I don't have to say much about ILE. I would only like to emphasize one of the overarching goals of ILE, which is to help students learn physics by thinking like physicists. And this means by engaging in the activities that mimic the actual practice of physics and using the reasoning tools that physicists use when constructing and applying knowledge. So I was lucky that I was invited to participate as a co-author in the second edition of the college physics book, Explore and Apply, authored by Aitken and myself and Van Heuvelin. And while working for this book, which is entirely based on ILE, I developed several new types of problems, which I will share today with you. I would like to also say that this is not only the book where problems are, but also in the Active Learning Guide, which is a collection of activities, and also the newly developed, just this summer, online Active Learning Guide that Eugenia and I developed. Then it comes also instructor's guide that helps teachers using this material, and more than 250 free videos that are supporting all this material. So let me start now with new types of problems. I will introduce new types of problems as they are named usually in the literature, like here, ranking tasks. And below you will see names of people that, or institutions, or just, how to say, the sources where I found them. This may not be complete, but I just wanted to emphasize that in most cases, we are not the authors of the types, but we developed also too, but we developed these problems that are known elsewhere for the purpose of the book. So ranking tasks. Here is an example of the problem of ranking task. You have 4 containers. They're filled with different volumes of water, and students have to rank the containers in order of decreasing pressure that water exerts on the bottom of the container. These red dots show the points where we are interested in the pressure. So this is a simple problem in which students have to apply their knowledge of hydrostatics. Specifically, they have to be able to contrast and differentiate between the volume or mass and the height of the liquid. So if they apply the knowledge correctly, they will realize that the highest column is in the beaker A, then beaker C, although the volume is the smallest here, then D and B, and also rank the pressures according to the from the largest to the smallest. So what are these problems good for? What is the benefit from these problems, what they develop? Oh, this is not the right, sorry. How is this? It was, okay, let me go back to now the right version, because in the previous version, yes, was too long. I adjusted it for this time slot that I have. So we start here. Ranking tasks. Students rank the pressures. What is the benefit of these ranking tasks problems? First, it develops ability to compare and contrast different cases, different quantities. This idea of comparing and contrasting is very powerful pedagogical tool. By comparing different things, we only understand what something is and how it is different from something else. So this is the main strength of this problem. Another ability which they develop, not this particular one, but other problems where we have only words. Students have to visualize the situations. In order to rank the different quantities, they have to have a picture of the problem of the experiment in their mind. And finally, they allow for various levels of achievement, which is very important for students to feel successful. What I mean here is that some students will only realize that, for example, this tallest beaker, the pressure in the tallest beaker is largest, and then they will probably confuse between C and D. However, the teacher has possibility here to give partial credits. So students don't have feeling that they failed, but they did something and they learned the rest from comparing their results with others. This is very important for those students who don't feel like belonging to physics. Often these are girls or minorities, that they are not that smart and so on. So for this purpose, it's very important to have problems that don't have just right or wrong, but problems that allow for different spectrum, so that they see, okay, I did it to some extent, but later I will do it more. Let's go to the next to the next type of problems. Choose answer and explanation. Here is a problem. We have a pendulum swinging back and forth, and we are asking, what can you say about the acceleration of the bob when it passes point P? And here underlined is choose correct answer and the best explanation. So here is one possible answer, and as you will see, all next answers have the same structure. Answer is the acceleration is 0 because the speed of the bob when passing the point P is maximum. So the structure is answer and explanation, and students have to find the option that has the correct answer and best explanation. Next possible answer is the acceleration is 0 because the sum of the forces exerted on the bob when passing point P is 0. The acceleration is non-zero and it points vertically up because the sum of the forces exerted on the bob while in constant speed circular motion points towards the center of revolution. Or the acceleration is non-zero and points vertically up because the string exerts the maximum pulling force on the bob when it passes point P. So you see, it's quite complicated for students. They have to, of course, read this first and then decide which option is correct. This particular problem connects two topics that traditionally we teach separately: circular motion and vibrations. As you see, the point which is oscillating, the simple pendulum, is the bob is moving along the circle. So students have to connect the knowledge from circular motion and vibrational motion. In other words, we are helping or encouraging students or developing the coherent knowledge. Coherent means that all parts of knowledge is connected together. So if they apply this reasoning correctly, they will realize that the correct answer is C. Acceleration is pointing upwards because this is part of circular motion. And the C is better than D because it describes the right cause-effect relationship. So this is because the bob is in a circular motion. Not every time when the maximum force is pulling on the bob is correct the answer, a correct answer in this case. So this type of problems find correct answer and explanation, develop ability to recognize the correct cause-effect relationship in addition to finding the correct answer, develop argumentational skills. Through reading these options, students also learn how to argument and how to explain and what is the right explanation and refine their feeling for explanations. Before going to the next one, I would like to add also that in my experience, I prepare future physics teachers. These are great problems also to give to future physics teachers at the end of the topic. So example, we finish electrostatics and you give to future physics teachers homework, create your own problem of this type, correct answer with the best explanation. It works really well. And you get also ideas from students. Next problem, evaluate reasoning or solution is typical for our book. And is one of those problems where students who are able to evaluate certain situation from different points of view are excelling. Several indicators are that often girls are good at looking at one situation from different points of view. So they are usually good in this type of problems. And that's why it's also good to have problems that are developing different abilities and also where different students can be good. So here is the situation. We have three friends. I'm not sure if you have snow in Indonesia, but I hope this is understandable. So these three friends are on the sled and they are on the hill, but the sled doesn't go down. So they are thinking of what to do to make the sled start moving. And here we put different statements, different reasoning into mouth of these fictitious students. Helge says, if one of us gets off, the sled will start moving. Steve says, we should invite another person to join us, and then the sled will start moving. And Heidi says, we should get off the sled, polish the bottom of the sled to make it smoother and sit back down, and then the sled will start moving. So the student have to comment on these suggestions, decide which reasoning is correct, but also explain using physics concepts and diagrams and so on, why those who were incorrect said what they did and indicate what part of their reasoning was correct. So you see, it's not only right or wrong, which is correct and which is not correct, but much more. What do we expect from students here is to analyze this situation using force diagrams, realize that the normal force and the static friction force also depend on the force exerted by Earth. So when somebody goes off the sled or somebody comes on the sled, simply all forces are proportionally changed and nothing changes. The only thing that really changes here, the situation is if we reduce the coefficient of static friction, and that's can be done by polishing the sled. But what is important is probably seen from this discussion, what this type of problems develop. So they develop ability to critically evaluate reasoning of some other person. That's very important in today's, the labor market today requires from us that we help students thinking critically and also ability to listen to others and listen to other ideas. Because often good ideas can be embedded in some maybe generally wrong statement, but valuable ideas can be found often by being able to detect critical ideas in some other people's ideas. Also, ability to recognize productive ideas when they are embedded in incorrect answers, as I already said. This develops also the feeling of tolerance, which is also important in our society, and search for productive ideas. There's another problem where of this type where students have to evaluate the solution. So in the previous problem, the student have to evaluate the reasoning, and here the solution provided by somebody else. So there's a problem. Friend proposes that a force diagram below describes the force exerted on a lawnmower during one instant while moving the lawn. The mower is moving to the right. So student has to discuss in a group, could such situation have occurred? And if so, describe the situation and label the force arrows on the diagram. But if not, explain why not. So we expect from students here to apply their knowledge. First to realize that the sum of the forces on the lawnmower is pointing to the left, but this sum of the forces only decide about the acceleration of the mower, not about the direction of the mower. So even if the mower is moving to the right, this diagram can still apply for the case when the mower is slowing down. And then they also have to mark and annotate the forces. This sort of problems, I showed you the problem where solution was given as a graph, but we have plenty of problems where solution is mathematical. So students have to go and through the solution, evaluate the solution. Evaluating means looking if the units are correct, if limiting cases are reasonable. So if mass is very large or it goes towards zero, does the equation predicts the reasonable outcome? And also if the numerical answer that at the end they obtain makes sense, is the right order of magnitude. For example, if we are talking about a person running on the street, the speed of this person certainly cannot come to 100 kilometers an hour. And also, again, students have to be able to visualize the situations. This is one of the abilities that we are constantly trying to improve, and that's why we put a huge emphasis on multiple representations and switching between the representations. And again, this type of problems again allow for various levels of achievement, as I already mentioned before. So here, students can recognize certain parts and maybe miss some others, and this allows teachers to still give partial credit to students. Jeopardy problems are very interesting type of problems that were initially created by Alan van Heuvelin and Dave Maloney. And these are problems where students have to go usually backwards. So from the solution that we give them or description, they have to think of what kind of a problem or what kind of situation, initial situation was that made this final result. So the most typical example are equation jeopardy problems. So we give student the equation and ask them to invent a problem that can be represented with this equation. So as you see in this case, one thing that students usually totally neglect, and teachers, become really important: units. So units here are like a fingerprints of the physical quantities. And from units, we only can recognize what this equation is representing. Second thing which is important is that you are very precise and strict here with notation. So we use regular font for units like kilograms, meters per second, and so on. But unknown quantities are typed in italics, like V on the right side. So what do we expect from student here? We expect the student to realize that this equation has two terms on the left side, and both are products of mass and velocity, and that velocity direction matters. That's why this -3 meters per second is here. And that again, on the right side, we have the same type of product, mass and velocity, but this time both masses are together. So this should remind students of the conservation of momentum, and then from here on they can create all kind of problems that they describe what happened and use the right units and right quantities in the description. Another type of problem from optics is that we give the location of object and image, but ask students to find which kind of a lens are we using, convex or concave, where this lens is, and what is the focal distance of this lens. So students have to do it backwards now, thinking of the array diagrams they were using in their problems, realizing that the ray that goes straight through the middle of the lens will not bend, and in this way connecting object and image gives you information about the location of the lens. And next they should remember that the ray that goes parallel to the optical axis will of course go through image, but where it crosses the optical axis, the parallel ray goes through focal point. So this allows students to find the focal point. If this appears difficult to you in all problems, have one thing in mind. All these problems require first the teacher practice these problems during the regular classes. So we never give these problems to students without seeing and practicing these problems before in the classes. And what we also do is we, when the first time teacher introduces a new problem, it's a good thing that teacher solves an example of the problem loudly. So speaking up, describing every step of reasoning in words to students, so the students see in details how an expert is solving this problem, what the expert is thinking. So Jeopardy problems develop ability to switch between different representations. I here showed only two, but there are many possibilities, going from electric field lines back to potential and electric field, going from energy bar charts back to graphs that describe velocity versus time and so on. So you have different representations, and switching between representations helps students develop coherent knowledge. This is also a type of problem that helps students describe their own ideas in words. We often hear from, for example, surveys like PISA and TIMSS, that students who are good in science are often not so good in literacy, so in describing their ideas in words or reading abilities and things like this. This is one type of the problem that encourages this, and where students and teachers have possibility to develop also the ability to express your ideas in words. This type of problems also develop ability to recognize physical quantities from units, as we already mentioned, and allows creativity and various levels of achievement from students. So students here are creative. They describe the problem, the situation, and they enjoy it. They love it. But for teacher to grade these problems is a little bit more difficult. It's quite easy pretty easy to compose these problems. You can practically take any traditional problem and turn it into this problem. But when you are grading students' work, evaluating, assessing the students' work, then you have to really make sure that you read and try to understand what they are trying to say, which is also good for teacher to develop this ability to listen to others and try to understand and find productive ideas in the text, which may be not written even with very nice handwriting. Next problems, actually one of my favorite, are tell-all problems. These problems describe a situation like this one here, for example. So you push a book, and it says 1.7 kilogram book, along a table, and then the book comes to a stop after a short distance. And figure below shows the acceleration versus time graph of the book, which was recorded by a motion detector. And now we say to students, say everything you can about this experiment. So open a question, anything you can using data that you have now here. So you have graph and you know that the book was 1.7 kilogram. This is like a detective story. Students are competing, and they're especially good for group work, and they are competing which group will find more quantities. You can again go deeper if you want. You can only ask students, just say which quantities you can determine, or you can say determine as many as you can and calculate 3 of them, or you can say just determine and calculate all of them. So what typically students find in this problem? Here I listed them from simple to those which are less obvious and more difficult to find. So some of the students will only read the graph. They will say, okay, from the graph, I know what is the maximum acceleration. I also know what is the slowing down acceleration. But even if they do only this, we see that student knows that in this case, the positive is the speeding up, the negative acceleration here is slowing down, and this is already evidence for some knowledge. Students can determine the interval in which the book was moving, then maybe more challenging to determine the maximal speed of the book, maximal force exerted by the hand on the book, friction force on book, coefficient of friction, and time, particularly where on this graph the hand stopped touching the book, is quite challenging. So another tell-all problem is this problem, which is formulated with the equation. So here we give an equation that describes variation of pressure at different positions and times relative to atmospheric pressure, and ask students to say everything they can about this wave. Now, again, students can determine the amplitude of the pressure variation, the period of vibration, frequency of vibration, which is just the 1 over the period, wavelength, speed of the sound, which they get by multiplying wavelength and frequency. And they also can determine in which direction the wave was moving compared to the direction of the x-axis. So this type of problems, ability to visualize the situation, this type of problems, tell-all problems, develop ability to, again, visualize the situation. You have to imagine what is going on and be able to turn that ideas into words. Ability to decide what is relevant and irrelevant. This is one of the abilities which is very important for labor market, for every job today. We are overwhelmed and we have too many usually data, and being able to see what is relevant is one of the abilities that is very useful. In these problems, there were not probably so many irrelevant data, but if you imagine, if you can give student a photo of the experiment and where there are plenty of data that are not relevant and some that are relevant. Ability to be aware of assumptions and their effects. This is a very important thing. If you think how often in traditional problems, students have to think about assumptions. Usually we just give them all assumptions. We say air drag is negligible and there is no friction and so on. we like to pose the problem and say, indicate any assumptions that you made. So then we see, okay, if student said that the friction is negligible and that he assumes that, then I will evaluate his solution according to this assumption. But being able to find the assumption, to be aware of the assumptions you are making is one very important thing for the scientists. In this case, for example, with the book, the assumption was, for example, that table is horizontal. If table is not horizontal, then the interpretation of the graph would be different. And again, this type of problems allow for various levels of achievement as problems we mentioned before. So we are almost at the end. I think we have two more types. Another type of the problem are multiple possibility problems. These are challenging type of problems, and again, problems that actually, as I say at the end, actually most of the problems in our life, real life problems, are multiple possibility. There's not only one correct answer. Here is a type of a problem. You have a V-shaped transparent container, and you shine a laser pointer horizontally through this empty container, and the beam goes through and makes a spot on the screen as shown on the picture below. And students have to think what happens to this spot if you pour some water in the container. And usually when we have this type of problems, we add this note. So we remind students, this is a multiple possibility problem. And again, you have to practice this type of problems before. So what we expect from students here is to realize how this different parameters, relevant parameters, affect the outcome of the experiment. In this particular case, the only relevant parameter that they can vary is the amount of water. So how would different amount of water produce different outcome of the experiment? Students will realize that if we don't pour enough water to reach the level of the laser beam, nothing will happen. If the level of water is just a little bit above the laser beam level, then it may happen that the beam gets totally internally reflected from the top surface of water and goes back, and actually the point would go a little bit down. Of course, here an assumption comes, and they can check it, because for water they may know the index of refraction and see if this the total internal reflection really occurs. But if we pour more water, it may happen that the total internal reflection on the top surface doesn't occur, and the beam goes out of the container, and the point is now much higher than the original point on the screen. The beauty of this experiment, and many of those that we created, is that you can actually, after students solve this experiment, perform the experiment in the classroom. And this is the most exciting thing, when they are now waiting, what will be the outcome? Am I correct or not? So all you need is a V-shaped container, and it's even better that container is a prismatic, so not like a cone, and you do this experiment. This type of problems, again, develop ability to visualize the situation. Here, in particular, they have to visualize the situation in many different scenarios. Again, ability to decide what is relevant, what is irrelevant, and again, allow for different levels of achievement. And again, note that most real-life problems are multiple possibility problems, and the challenge for teacher here is to find problems that are reasonable but simple enough. So it's not problem finding these problems, but finding the right problem is a problem. And the next type of problems are problems that require from students to make judgments based on data. Here is an example. Somebody tells you that figure below shows a displacement versus time graph for carts on linear track before and after collision. And when the friction and air drag are negligible, and the masses of carts are given. And students have to decide, based on this data, is the graph in agreement with the laws of physics, and explain their reasoning. And if they think that it is, then they should also say if this collision is elastic, inelastic, or totally inelastic, and explain. This is the problem where students are not told what law of physics they have to think of. They have to realize that in any collision, inelastic or totally or elastic, law of conservation of momentum should apply. So they have to check if the law of conservation of momentum here in this case is valid. And to do this, they have to first determine the total momentum before and after the collision. They have to first get values of the velocities from graph, read the graph from inclines, determine the velocities, and then determine if the momentum remains constant in this case, because there is no force exerting on the system from the environment. The total momentum should be constant. And then in the next step, decide if this is elastic collision, then total mechanical energy remain constant in the experiment. This type of problems develop ability to make judgment about one or more hypotheses based on data or other forms of evidence that are given to the students. And sometimes we also include uncertainties. Students with this problem learn how to reject a hypothesis. Think of how many times in school students in traditional teaching are required to reject a hypothesis. In most cases, we only give them the processed truth, and usually they would only check if something is according to the theory that we learned before. While in the real life, scientists have to do, the most challenge is to reject the hypothesis, and this is an ability that is very important. Students also learn how to question authority. They have to be prepared to say, no, this is not correct, which is not only important for physics or science, but in everyday life. And finally, the last example are problems that are based on the real experiments with easy available equipment. Here is just an example of the problem. So you place a point-like source in front of the convex and concave lens, and you observe what you see on the screen. And students have to explain qualitatively how these patterns are formed using ray diagrams. What we expect from students is now to use ray diagrams, but not in that conventional way that we usually ask them, those 3 rays, but to draw more rays, to be aware that this point source is emitting infinite number of rays, and that some rays are missing the lens, and some rays are going through the lens and bent. And from this, they realize where, on which parts of the screen, the density of rays that come is larger or smaller, and from that determine the intensity at the different parts of the screen. These types of problems combine ability, again, to switch between different representations, but also help students learn how to use modern devices. In this experiment, for example, we were using white LED, and how to investigate phenomena and how to construct simple experiments. So what we do, we give problems that are so simple that students say, oh, I should try this. And this, at the same time, are also the challenges for students to work by themselves. So this brings me to the end of my talk. I would like to summarize just 3 main ideas our duty is not only to help students learn physical concepts, but also to help them learn how to think like physicists. And problems that we are using to assess students' knowledge should be consistent with these learning goals. So if the society and the labor market expects from us to develop new types of abilities and skills and competencies, then our teaching and the problems that we are using should reflect that. New types of problems require new ways of learning and teaching. Again, I emphasize, if you're excited about one type of problem, first practice it with students and then give it to them. Don't give them straight away before, making sure that they've seen at least some examples before. And finally, IEL approach is useful for creating new types of problems. In all these problems, the philosophy of IEL, what to ask, how to ask, what the sequence of questions that is best working, was all because of IEL approach that I learned from Virginia and Alan and used in these problems. So thank you very much. Greeting from Ljubljana. This is a view of the town of Ljubljana from the little hill above the city. And I'll be happy to answer your questions.
Professor Gorazd, Planinsic, for you very interesting presentation about the new type of the problem
I think we still
to
have
face
some.
the
Thank you so much, Gorazd.
21st century. We have one question. We have one question.
But yeah, okay, here we go.
We have one question from Didi Sugeng Pambudi MSc. He say, thank you for many kind of interesting problem which oriented to higher order thinking, hot. But in fact, in Indonesia, so many students doesn't have high motivation to solve this problem. Would you like to explain us how to make students interested to solve the problem, especially from your experience in your country? Thank you.
I don't hear your.
Huh?
Please unmute yourself,
Okay.
Irwandi.
Okay. This is one question from Dr. Nak terdengar juga. Hello. Hello. Are you listen? Are you listen?
Are you listen?
Okay. Double suara. From a question from Dr. Didi Sugeng Parbudi. Thank you for many kind of interesting problem which oriented to high order thinking skill, hot. But in fact, in Indonesia, so many students do not have high motivation to solve this problem. Would you like to explain us how to make students interested to solve the problem, especially from your experience in your country? Thank you.
Thank you very much. I understand understand the question. Yes, and I must say that many of my teachers, when I presented this type of problems in the continuous education program that I run for in-service teachers who are already teaching, had similar feelings. Let me first say that we as a people all perceive something that is new to us as difficult. So this is the first thing that you have to be aware. If you think that your students are not able or not have motivation for this, you might be under impression because this is new to you. I'm talking this because it same happened to me. I said, no, students will not be able to do that. And then Eugenia said, try, give them and see what will happen. And often they surprised me. Often they surprised me that actually they were able to solve problems that I was not expecting that they will be able. However, I would say again that if teacher doesn't do these problems before in the classroom and introduce them in each topic, then of course you cannot expect for some type of problems the students to be able to solve them. What is important is also to realize that I showed you now here all this number of problems. Of course, it would be impossible to start using all of them at once. Start at the type of problem that looks most, let's say, interesting or familiar, or the problem for which you think that would be easiest for your student. Start with that one, and then add next one, and then next one. So, and also not every topic is suitable for this type of problems. You will see if you search through our book, in some topics of physics, some types of problems are more frequent than in others. So I would say start, and you will see that students like it because it's a challenge. But in order to achieve this challenge, you have to make them feel successful. So this means that you have to acknowledge partial credits, small steps, and also that you have to prepare them first, give them all the tools that they will be successful later. If they are successful, they are motivated.
Okay. Thank you, Gorazd. And also my experience during my teaching to the student to face, this is the basic understanding, like Islam. This is the very important, because this is the new type of the problem, In Indonesia, we focus to solve the problem, not to understand. But now I try to teach, it's better to understand than solve the problem. Because the problem in the future, we have to understand first to solve many problems in the future. Okay, thank you, Gorazd, for this. This time is close at the 3 o'clock. Thank you for your time to participate in this system 2020 conference. This is the very nice meeting for you. I hope in the future we can meet again for another moment. Thank you, Gorazd.
Thank you very much, and thank you again for invitation. It was an honor and pleasure to participate in your conference, and I wish you successful completion of the conference, and hope to see you somewhere in presence in time when this situation is improved.
Okay.
Bye-bye.
Bye-bye.